What I want to talk about today is the RGB color space. Now let's begin by defining a few terms. By color space, I mean a formal system for characterizing color. And RGB is just one of many examples of that. For example, XYY is a color space, XYZ is a color space, LAB is a color space, we could go on and on. This is not to be confused with the various gamuts like Rec. 709, which define the limits of color performance or color reproduction. But it's a formal way of characterizing color. Now, I want to talk about RGB because it has some unusual characteristics. One characteristic of RGB is that it is gamut specific. So what that means is that whatever RGB values you use to characterize a color have meaning only in the context of a specific specified gamut. Now I've included a gamut in this spreadsheet, the 709 gamut or high definition gamut, which is arguably the most commonly used. If we were to change this gamut, then whatever RGB values we had for a particular color would also change. Okay, so that's one unusual characteristic of RGB. A second unusual characteristic of RGB is that it has two versions. One version is RGB with gamma, and that's expressed in this first set of RGB prime values here. And then the second type of RGB is RGB without gamma. Linear RGB. So let's start with a simple example. So let's take a color that we are commonly familiar with and see what sort of RGB value is derived from that color. So let's use the standard white point for both Rec. 709 and Rec. 2020. And that is 0.3127, 0.329, 1.0. Now, the only math that's involved here of any significance at all is that before you do anything by way of converting white into RGB, you first have to convert the XYY value into XYZ. XYZ is the fundamental component of the 1931 color system that is still widely used. XYY, which is the one we're more familiar with, is really just a mathematical transform of XYZ that allows us to express a color on a chromosticity chart. So when we see colors plotted on the tongue-shaped chart, the CIE chart, those numbers are expressed in XY, lowercase x and lowercase y. But they're the same colors that would be originally characterized in XYZ. In any case, before you convert from XYY to RGB, you first have to convert XYY into XYZ. And so here's really the only math that's involved. So let's start with X, and the formulas for converting first XYY to XYZ and then the reverse XYZ back to XYY are down here. So let's start with X. So X is paren small x times big Y close paren divided by small y. There, that enters the value. Now, y, uppercase Y, is the same. It's the same number, so we just copy that over. Now, Z is the most complicated conversion. It's a double paren 1 minus x minus y close paren times uppercase Y, close paren, divided by lowercase y. Okay, there is the same color, except now expressed in a different color space. We've taken the same color and converted it from XYY to XYZ. Now, once we've done that, we can now proceed with the task of converting this color into RGB. And it's worth pointing out that unlike RGB, which has both a gamma-weighted and a linear version, XYY and XYZ have gamma by definition. So the first conversion that we're going to accomplish will give us gamma-weighted RGB, RGB with gamma. So in Excel anyway, here's how you do this. First, highlight the 3 target cells. And then we're going to pick a formula. So the formula is immult. And what this does is it multiplies one matrix by another. So click OK. And the first matrix array is our originating XYZ. The second matrix array, if you go over here, we have the 709 gamut, first expressed in XYY, then converted to XYZ, and then XYZ has been inverted. And I'll show you how to do that in a second. So the second array in this formula is the inverted XYZ of the 709 gamut. So we highlight that, all those cells, and I'm going to make this an absolute reference, which is not really necessary for this explanation, but if you ever wanted to copy down the values, that would be essential. And now, to enter the values, you have to press Control-Shift-Enter on the keyboard. And there. Now, isn't that interesting? So, what this tells us is that in the 709 gamut, the white point is equivalent to equal values at 100% of RGB. And that's exactly what you'd expect, right? RGB are equally weighted, so you don't see any color at all. You see neutral white. Now, let's make one small difference to this, one small change to this conversion, because we're going to have to avoid problems in the, when we do our next calculation. So what I want to do is, let's highlight these again, and let's go up to the formula up here. And all I'm going to do is I'm going to round this. So that's a simple formula, just round. And then I'm going to say I'm going to round it 3 places, which, since we're using parentheses here, excuse me, since we're using percentages here, that's just going to be 1 decimal place. And I'll close that off. And then to enter this, again, you have to press Control-Shift-Enter. And now all 3 of these have been rounded. They don't change because we're only using 1 decimal place here anyway. Now, the reason we did that is because if you don't round it to that, I could have shown you that if we kept calculating these values out to increasingly larger number of decimal places, at some point you'd find that one of these colors, in this particular case I think it's green, is not exactly 100%. It's like when you get to the 8th or 9th decimal point, it's, 0.8 instead of 0. So the next conversion to linear RGB gets screwed up because of that. So we've made it now exactly 100%, 100%, 100%. Now, the last stage to convert from gamma-weighted RGB to linear RGB is really simple. All you do is reference the value, and then assuming we're in a 2.2 gamma, 2.22 gamma, and I'm just using this for illustrative purposes, I want to not add gamma because we've already got gamma there. I want to remove it. So you do that by taking the power of the reciprocal of 2.22, which is this number here. And the way that you derive here, let me do it first and then I'll show you how you derive it. Again, let me make this a absolute value so I can copy it over. And we get the same values. Now the way you get that number is you just do 1 divided by whatever the gamma is. And that same number. That's called d gamma. So that's with gamma removed. Now in this particular case, it doesn't really tell us much because we have the same values in both cases. But that's only because we're working with 100% here. So let's work with something other than 100%, because when you have 100%, gamma doesn't matter. Gamma only comes into play when you're dealing with something less than 100%. So instead of this being 100%, let's make it 75%. Very different values. Starts off with 75%, and once we take away the gamma, it's 87%. Now that's actually a little misleading because 75% would not in the real world be represented by 0.75 because, again, we're using gamma. So 75% is going to be something a little different. So let me show you how that works. So let's assume that the original number is 1.0, which is what 100% is. And we want 75% of that with a 2.22 gamma. And so instead of 75% in the originating number, it's actually going to be 52.8%. So let's enter that value. There, that's the way the calculation would work in the real world. So we start with 52.8%, and once gamma is taken away, then we get to the linear values, which are 75, 75, 75, or just 75%. Now this works not just for white, but it also works for colors. So for example, let's take red, and we can see what red is over here on the right in the gamut definition. So red is 0.64, 0.33. And let's make this a little more interesting. Let's again make this 75%. So the only thing we need to change is the original is not 1.0, it's this number. That's the maximum luminance of red in the Rec 709 gamut. And so the number here is, rather than typing it, I can just reference that value. Okay, that's 75% red. Now we can just copy down these two values. That gives us the XYZ of red. And I think I used absolute values here, so I should be able to copy this down. Yeah. And then same thing here. So this is actually very commonsensical. So red at 75%, and that's with a 2.22 gamma. So if we use a different gamma, here, let's pick 2.35, you get different numbers. So what that means is you get different values with the gamma weighted RGB, but notice the linear RGB stays the same. So instead of being 75%, 75%, 75%, Now the value is 75% red and 0% for the other two colors, which is exactly what you would expect. Now, I said earlier that I would explain how you get the inverse values of the target gamut. So here's how you do that, at least in Excel. First, and by the way, notice that when I say gamut, I'm just referring to RGB. You don't need to worry about the secondaries or even the white point, just the RGB values. First, you highlight the target cells, which is going to be a 3 by 3 matrix. And then you go to your list of functions and you pick M inverse. And then you just pick the particular 3 by 3 matrix that you want to invert. In this case, it's the XYZ of the 709 gamut. And let me make that an absolute reference. And then again, because this is what Excel calls an array function, you have to type Control-Shift-Enter, on your keyboard in order to get it to take. And here, let me make this font a little smaller. Yeah, this is it's the exact same values that we have up there. So that's how you get an inverted matrix.